back. In this video, we're going to go through another application of differentiation. It's simply finding the inflection points for a graph of a function. And here's our function 6 sine x plus 6 cosine x. And we're going to investigate the points of inflection in the interval 0 and 2 pi. At this moment, I just want to remind you what points of inflection are. Well, first off, this is very similar to the critical points idea when we use the first derivative test. So critical points were telling us whether the function is turning from increasing to decreasing behavior or vice versa. Inflection point is a point that makes the second derivative 0 or undefined. And it's very similar to critical points because critical points were the points that make the f prime function 0 or undefined. So now we're looking at f double prime, whether or not if there is a c that makes the function 0 or undefined. We need the second derivative of this function to continue with. So why don't we go ahead and hit the road by finding the first derivative of the function. And here we go. The first derivative of the function is 6 times the derivative of sine plus 6 times the derivative of cosine. And it's the time to check for the rules of differentiation or the formula card for differentiation, just to check for the derivatives of sine and cosine. And it turns out to be that sine has a derivative of cosine and cosine has a derivative negative sine. So this should be minus sine x. So this is just the first derivative. We need the second derivative, which is the derivative of f prime, is 6 times cosine x prime minus 6 times sine x prime. And from the same formula card, you can read that cosine has the derivative negative sine. So this is a negative 6 sine x. And sine has a derivative of just cosine. So we have negative 6 cosine x. All right, we are looking for points that make f double prime either 0 or undefined. Since the second derivative of the function is negative 6 sine x minus 6 cosine x, and we know from pre-calculus that sine x and cosine x are defined for all x on the real axis. So in fact, there is no x that makes f double prime undefined. So no x. So no contribution for an inflection point from this condition here. All right, we set this expression to 0 and send one of the terms to the right-hand side and divide by cosine x. And you have minus sine x over cosine x equals 1. Well, we have sine x over cosine x to be equal to tangent x. That's the definition of tangent. So we have tangent x essentially equal to negative 1. So now we're looking for x's whose tangent is negative 1. You can go ahead and use the unit circle for that because our interval is 0 and 2 pi. If you use your TI-84 to find this, you will have negative pi over 4 in the output, but negative pi over 4 is not in this interval. So what we can do here is that we can add pi and 2 pi to get the same terminal side for the angle negative pi over 4. One should be equal to 3 pi over 4, the other one should be equal to 7 pi over 4. To sum up, we found the second derivative of f, and we checked for any x that makes f double prime undefined, so we got no x for that. And we set f double prime to 0, and we found two different values, 3 pi over 4 and 7 pi over 4, and these are the x-intercepts of f double prime. In other words, they are called inflection points. Now we're going to go ahead and check for the sign of f double prime to determine about the concavity of the graph of the function. And here we go. We have the endpoints 2 pi and 0 over there, and then we got two inflection points, 3 pi over 4 and 7 pi over 4. You can go ahead and find the corresponding y values or function values at those points. They're going to be 0 essentially. And now we're going to choose sample points. All right, so within this interval 0 and 3 pi over 4, I got pi over 2 and pi and 15 pi over 8 from here. You can choose different sample points as you remember. And next we evaluate the second derivative of the function at those sample points. So that's a good exercise for you now, that you can check f double prime at pi over 2 and pi, and 15 power 8 by using your TI-84. And convince yourself that f double prime is negative here, positive here, and negative here. And applying the concavity test, we conclude that f, the function itself, is concave downward in this subinterval, concave upward on this subinterval, and concave downward in the last subinterval. So here is our conclusion. So only concave up in the middle here, 3 power 4, 7 power 4, and concave down on 0, 3 power 4, and 7 power 4, and 2 pi. Remember that we were supposed to write down the concavity or concavity behavior over the interval. So we had to use the interval notation here. And finally, we have the graph of the function to convince ourselves about what we got in the table. So here we go. We have up here on the left of this inflection point, as you see that the function's graph is concave down. So here it's increasing up here and then decreasing. Since we didn't check anything about increasing, decreasing behavior, so we don't really know where it's increasing or decreasing. We only check for concavity in the table. So as you see, concave down across this point becomes concave up all the way forward. And since we have another inflection point here, the concavity is going to change for sure, and it's going to go like this, and then it's going to be a concave downward pattern. All right, we verified our table by checking the graph of 6 sine x plus 6 cosine x, and that makes the end of the video. Thanks for watching. I'll see you in another video. Bye.